welcome to Quantum Online Academy. This is your Dr. Nagaraju Pendem. In this video, we have to discuss about the Deuteron problem. It is very important in nuclear physics. Not only in nuclear physics, in daily life also. Deuteron problem is very important. Clear? In this entire the Deuteron problem we are not discussing. Okay. Two important things we have to discuss. One is binding energy of the Deuteron problem. The second one is spin and parity of the Deuteron problem. Two things I want to discuss about the Deuteron problem. What is the Deuteron? It is a isotope of the hydrogen, right? What is the chemical composition of the Deuteron? It is the isotope of hydrogen. That chemical composition is 1H2. 1H2 is the Deuteron. Chemical composition of the Deuteron. 1H2. Right? Clear? 1H2 is the chemical composition of the Deuteron. Suppose if you break the Deuteron, suppose you break the Deuteron means how many protons are there? That proton number is equal to number of protons is equal to how many protons are there? Only one proton is there. How many neutrons are there? The number of neutrons is equal to the number of neutrons. How many neutrons are there? A minus Z neutrons. A is equal to 2, Z is equal to 1. 1 neutron is there. If break the Deuteron, 1H2 is equal to 1 proton plus 1 neutron it will come. How many protons, how many neutrons it will come? 1 proton and 1 neutron it will come to break the Deuteron. Clear? To break the Deuteron, how much energy is needed? That energy we call it as a binding energy. To break or to collision or to coherence, such type of energy we call it as a binding energy. How much energy is there? We have to calculate once. You have to see the binding energy of which one it is? Binding energy of Deuteron. Binding energy of Deuteron. Which one it is? Binding energy of Deuteron. That binding energy of Deuteron, how we have to calculate once you have to see. First you write the equation. Deuteron 1H2. It consists of 1 proton plus 1 neutron is there. First to calculate the binding energy, how we have to form the binding energy? By using a mass defect. First we have to calculate the mass defect, right? Delta M is equal to delta M, mass defect. First you have to calculate mass defect. Delta M is equal to initial mass of the Deuteron minus final mass of the Deuteron. First initial mass of the Deuteron. The initial mass of the Deuteron Mi of which one? 1H2 is equal to the initial mass of the Deuteron is equal to, I will give that value is 2.014104 atomic mass unit. Which one it is? The initial mass of the Deuteron. Now we have to calculate a final mass of the Deuteron. Final masses are, how many masses are there? 1 proton is there. Final masses of the Deuteron is equal to mass of the proton plus mass of the neutron. How many masses are there? 1 mass. 1 mass of the neutron. Therefore, we have to write 1 into mass of the proton is equal to 1.00782 plus 1 into mass of the neutron is equal to 1.00866. You have to add these two. How much you have to get it? 2.016290 AMU you have to get it. How much you have to get it? 2.016 into 290 AM. Now we have to calculate the delta M is equal to Mi minus Mf. Mi is equal to 2.014104 AMU minus 2.016290 AMU. How much you have to get it? This one is lesser value compared to this value. That's why minus 0.00 minus 0.002386 AMU you are getting. 2386 AMU are getting. One thing you have to see, what we have to discuss in this year, right? Here mass of the mass means mass defect. Mass defect, how much we have to get? Mass defect delta M is equal to minus 0.002386 AMU we are getting. Correct? 2386 AMU we are getting. Right. If delta, one logic I am telling, if delta M is equal to negative, if delta M is equal to negative means the energy is needed to break the nucleus. If it is negative means energy is needed to break the nucleus. Needed to break the nucleus or deuteron to break the nucleus. If it is not like that, or delta M is equal to mass defect is equal to, if it is positive, what is the happening? Energy is released. If it is positive, energy is released to break the nucleus. To break the nucleus, when the nucleus is broken, the nucleus, energy is released, nucleus is broken. Nucleus is broken. When the nucleus is broken, energy is released. If it is positive. Here negative we are getting. How much energy is given? You have to give some energy, then only the deuteron is break. Now we have to calculate that one. How we have to calculate? Once you have to see. Delta M we found the binding energy of the deuteron is equal to, delta M into C square. This is the Einstein mass energy principle. Which principle it is? Einstein's mass energy equivalent principle. Mass energy equivalent principle. Right? Which principle it is? It is the principle of Einstein mass energy equivalent principle. So in this principle, once you have to see, the binding energy of the deuteron is equal to, what is the mass defect we are getting? 0.002386 AMU into, what is here? C square you have to take. Right? 0.002386. 1 AMU is equal to 931.5 mega electron volt is divided by C square into C square. You have to cancel it, C square into C square. You have to multiply this 0.002386 into 931.5. You will get 2.226 mega electron volt. What is the binding energy of the deuteron? Binding energy of the deuteron is equal to, or suppose are equal to, you have to make it as a whole number, 2.23 mega electron volt, right? To break the nucleus of the deuteron, how much energy we have to give? 2.23 mega electron volt we have to give. This is the deuteron binding energy. Clear? Very, very important. Once again I am telling, once you have to see what is the deuteron. Deuteron is the combination of proton and neutron. Clear? Deuteron is the combination of the proton and neutron. We have to break or we have to form. We will give some energy, we have to release some energy. Such energy we call it as a binding energy. Now we have to calculate the binding energy. Before going to the binding energy, why binding energy is getting? Because of the mass defect. Because of the mass defect, binding energy is arises. That energy how we have to calculate. If it is mass defect is negative, energy is needed to break the nucleus. If mass defect is positive, energy is released, nucleus is broken, right? Now you have to see what is the binding energy. 2.23 mega electron volt. Now we have to discuss the second one. What is the second one? Already I told. Two important things I want to teach. The second one is spin and parity. Spin and parity. How we have to calculate the spin and parity? The spin is J and parity is 5. The spin and parity of a deuteron. Which one it is? Deuteron. Spin and parity of the deuteron. How we have to calculate the spin and parity of the deuteron? This is very, very important. So many times, so many competitive people are asking this question. What is the spin and parity of the deuteron? Clear? Not only spin and parity, quadrupole movement is there, electric dipole movement is there, and then the wave function equation is there. So many parameters are involving in the deuteron problem. But in this video, I choose only two things. One is binding energy of the deuteron. The second one is spin and parity of the deuteron. First, binding energy of the deuteron we finish. Now we have to go for the spin and parity. How we have to calculate the spin and parity once you have to see. First, deuteron you have to write. In this deuteron, you have to write the components. How many protons are there? How many neutrons are there in the nucleus? How many number of protons? Number of protons in deuteron is equal to number of protons. Z is equal to how many are there? Only one proton. This is the odd one. One is a odd. So that's why we have to take the configuration, right? Proton configuration we have to write. Next, number of, which one we have to write? Number of neutrons. Number of neutrons, what is the formula? A minus Z. A minus Z is equal to 2 minus 1 is equal to 1. 1 also odd number. 1 also odd number. We have to write both. Any even is there, we have to diminish it. Both odd is there, we have to write the both we have to consider. First we are writing the proton configuration I want to write. Which one we have to write? Proton configuration. You have to write the proton configuration. Configuration. Which one we have to write? Proton configuration you have to write. What is the proton configuration once you have to see? How many protons are there? Only one proton is there. Where we have to keep the first proton, we have to keep 1s1 by 2. 1s1 by 2. In this state we have to keep. How many protons? Only one proton is there. That proton we have to keep. L is equal to, if it is S is S, that's why L is equal to 0. Right? J is equal to, how much J? This is the J value. J is equal to 1 by 2. This one L1 we have to write. This one J1 for proton we have to take. Next, which one we are writing? Proton configuration we are writing. Next you have to see Neutron also odd number. Neutron configuration also you have to write. Neutron configuration. Which one we are writing? Neutron configuration we are writing. How many neutrons are there? One number of neutron is there. What is this configuration? This configuration also 1s 1 by 2. If s is equal to s, that's why L2 is equal to 0. And what is the j value? J is equal to, J2 is equal to 1 by 2. Now we have to calculate the nuclear spin. Now we got the L1 is equal to 0, J1 is equal to 1 by 2, L2 is equal to 0, J2 is equal to 1 by 2. Which one we want to do? We want to calculate the nuclear spin. How we have to calculate the nuclear spin? The total nuclear spin, if it is both are odd, by using the LW Norim rule. What is LW Norim rule? So you have to see what is that one? LW Norim rule. LW Norim rule indicates what it indicates? J is equal to L1 plus L2 plus J1 plus J2. What is this J? This J is the nuclear spin. I or J is equal to, you have to get L1 plus L2 plus, first you have to calculate L1 plus L2 plus J1 plus J2. L1 is equal to 0, L2 is equal to 0, J1 is equal to 1 by 2, J2 is equal to 1 by 2. So you are getting how much value? 1. 1 is even or odd? This value also odd. If L1 is equal to L2 plus L2, J1 plus J2 is equal to, here two functions are there. If it is odd, that nuclear spin is equal to modulus of J1 plus J2. Modulus of J1 plus J2. If it is even, so when this value is even, J is equal to modulus of J1 minus J2. What value we are getting? Odd value we are getting. Therefore, J is equal to which one it is? 1 by 2 plus 1 by 2. This rule is not existing here. J is equal to 1. What is the nuclear spin? Nuclear spin is equal to J is equal to 1. This is the nuclear spin. Nuclear spin of whom? Nuclear spin of deuteron. Clear? Nuclear spin of deuteron we found. Very, very important. What indicates if both are odd, we have to follow this rule. What is that rule? LW Norim rule. In LW Norim rule, first you have to calculate L1 plus L2 plus J1 plus J2 you have to calculate. Whether you get the odd, you go for this rule. Whether you get the even, you go for this rule. We are getting the odd, 1 is a odd number. That's why we are following J is equal to modulus of J1 plus J2. Therefore, J is equal to 1 by 2 plus 1 by 2 is equal to 1 we are getting. Clear? So, this is the thing. What is the nuclear spin of a deuteron? 1. Next, we have to go for the parity. So, what is the parity? If it is both are there, both angular momentums are there, that parity is equal to the parity formula. Parity, how we indicated 5. Parity is equal to minus 1 to the power of summation of L. Pi is equal to minus 1 to the power of summation of L means L1 plus L2. Therefore, phi is equal to minus 1 to the power of L1 is equal to 0 plus L2 is equal to 0. Therefore, minus 1 to the power of 0 is equal to, you are getting the positive, that is a positive spin. Parity. Which parity? Parity is the positive. Clear? Parity is the positive. How we have to implement spin and parity? Spin and parity, we have to represent like this. J5, J is equal to 1, pi is equal to plus. What is the spin and parity of a deuteron? 1 plus. This is very important. Like this questions we will get in your competitive exam. This is very important area. The spin and parity and the binding energy. Two things we discussed. The binding energy of the deuteron. The binding energy of the deuteron is equal to how much we are getting? 2.23 mega electron volt. The spin and parity of the deuteron is equal to the spin and parity of the deuteron is equal to 1 plus. Very important. So please share and subscribe our YouTube channel. The channel is for you only. You have to learn the physics and enhance your physics knowledge. How to solve the physics questions. You have to learn how to solve easily physics questions. Thank you so much.